Hello, this is Jack Jackson again, and we're going to continue our lecture on functions. If you remember in part 1 of this lecture, we talked about defining a function. And remember, our definition of a function was a set of ordered pairs, a relation, in which no two of the first coordinates were the same. And so we saw what that would do and how that would be represented in various different ways that we looked at relations. That is, by tables, formulas, graphs, various kinds of graphs, various kinds of rules, and so forth. Today we're going to continue on with talking about functions. And the topics we're going to talk about in this part are independent and dependent variables and coordinates, function notation, because there's a special notation we use just for functions that we don't use for relations in general. Briefly, we'll talk about onto functions, the natural domain of a function, and evaluating functions in the various different representations. So let's take a look here at an arrow diagram again, and we have some relations here. So the one on the left, notice, is a relation that's not a function because, well, both the 5 and the 9 in the domain go to two different points in the range. Whereas the one on the right is a function because every element of the domain is mapped to a single element, a unique element in the range. So no repeats in the first coordinates on the right, but there is a repeat, a couple of repeats actually, on the function on the left. So now what I want to do is choose an input from the domain. So if we do that on the one on the left, the one that's a relation that's not a function, we've got some choices. We can either choose, well, we can choose any element that we want from the domain. In this case, that's either a 2, 4, 5, or 9. So let's just pick one. Let's say I pick 5. Okay, so then I want to choose an associated output. Well, notice that I have, if I pick 5, I've got two outputs possible, a 4 and a 6. Yeah, sometimes I feel like a 4, sometimes I feel like a 6 if I start with the 5, or I feel like both. So now it's not quite so, it's not real determined. There's still something left up in the air even after you pick the first coordinate. There's still something to be decided and chosen to get to an ordered pair for the second one, or there are two different paths to choose. A little more wishy-washy. Functions, on the other hand, are decisive. Look at the one on the right. It really doesn't matter which one we pick. Now notice we still get a choice for anything we want, so we have an independent choice of what we pick for the input value, so anything from the domain, either A, B, or C. But once we pick one, we only have one choice for the output. So if we choose A, we have to go to 4. If we choose B, we have to go to 2. And if we choose C, we have to go to 4 for the second one. So the second coordinate doesn't allow any choice whatsoever, or only the one choice, I guess I should say, where the only choice that we have is really for the first coordinate. Once that first coordinate is fixed, it is very decisive. So functions are very decisive. They're not quite as wishy-washy or indecisive as a relation might be. Okay, so this leads us to some terminology that we use for functions, not necessarily for relations in general, but for functions. So remember, in relations that are not functions, there's at least one choice of input that allows two or more choices for the associated output. But functions are decisive. In functions, we have a free choice of the input with potentially many choices. However, once the input has been chosen, there's always exactly one choice for the output. So the output completely depends on the choice of the input, and of course the definition of the function. So in functions, we call the input the independent coordinate, and when we put a letter that goes with that for the variable, we call it the independent variable. And we call the output the dependent coordinate, and the variable going with it the dependent variable. So the output completely depends on the input. So input, our first coordinate, is called independent coordinate because, as we saw back here, we can choose A, B, or C here. We have a free choice. It's independent. But once it's picked, the output depends only on which one we pick here for the input. So the output is called the dependent coordinate or the dependent variable when we put a letter with it. Now, because the output depends completely on the input, we're going to introduce a notation that's going to emphasize this, and it's only used for functions. So first of all, recall that for relations in general, the generic, basic letters, bland letters, are x for input, y for output. For example, we might write an equation as x squared equals y squared. That would be a relation in general. But if it's a function, we will still continue to use x for the generic input variable, but we'll use f for the dependent variable. So instead of writing, say, y equals 3x, we would write f equals 3x. And then we're going to go with one more step. Instead of just calling it f or y, we're going to call it f of x. That's f open parentheses x close parentheses, and that's pronounced f of x. Now, f of x is just a more complicated way of writing f, or just y. Now, at this point, you're probably thinking, okay, so why did you do this? I mean, you just made it more complicated. You wrote f, there's all this f of x. Why'd you do that when you could have just got by with just saying f? Or, for goodness sakes, I'm more comfortable with y, just leave it y. Well, the reason is, well, there's two reasons. One is that this emphasizes the fact that for functions, the output f depends entirely on the value of the input x. So when I say f of x, I'm saying f depends on x. So once I choose an x, the f is uniquely determined. So I can choose any x that I want from the domain. That's independent, but the f depends on the x. And it's notationally convenient. So whereas we might say f of x is just f or y or whatever we want to label the output, okay, that's sort of the generic output or general output. But if we put a particular number in that parentheses, then we're specifying that number in the parentheses is the input, and the f of that is the output that goes with that. So, for example, when we write f of 4, that's the particular f value, y value, output, associated with the input value 4. So f of 4 is f, it is y, it is output, it is second coordinate, but it's the specific second coordinate output, y, f, that goes with an input of 4. So the ordered pair is 4, comma, f of 4, whatever f of 4 is. So again, for relations in general, generic letters used are typically x and y, but we would prefer to use other more suggestive letters in our applications. For example, T for time, V for velocity, P for unit price, R for revenue, so forth. For functions, the generic letters are x and f, or f of x instead of just f. But we'd also like to use more suggestive letters there. Again, if it was velocity and time, it might be T for input and V of T, V or V of T, for the output. We typically name functions with single letter names, such as function f, function g, function h, but some specific functions have longer names, like we're going to talk later in the course about a function called ln, the natural logarithm function, or exp, the basic exponential function, or abs, the absolute value function. Or these next two we don't talk about in this course, but in a trigonometry class, we'd talk about the sin, the sine function, or tan, the tangent function. So when you see tan of x, it's just like f of x, or ln of x is like g of x, whatever. But it's a specific function. Now, the fact that we can use multiple letter names, like we can talk about functions f, g, and h, allows us to have multiple functions considered at the same time, and we can tell them apart by which letter. So we could say, well, f of x is given this way, and g of x is something else, and h of x is something else. And so then if we talk about f of 3 or g of 4 or h of 4, we know that those are which function that those are coming from, which relationship that gives that. And so by choosing different letters, that allows us to kind of consider different functions at the same time. Okay, so let's see if you've been paying attention here. I've got four different equations here. Y equals x squared, v equals t squared, f equals x squared, f of x equals x squared. Which of the following are the same functions and which are different? And are they actually functions, or some of them relations that aren't functions? But which ones of these represent the same thing? Let's let you think about that a second. Come up with your answer. Press pause and then come back. Press pause now. Well, let's take a look here. In the first three lines, we got y equals x squared, v equals t squared, f equals x squared. All we did is change the letters. They still have just a basic letter on the left equals a basic letter to the second power on the right. And so as long as the letter on the right, whether it's x or t, is the first coordinate or the input, and whether it's call it y or v or f, as long as that's a label for the output, then these are exactly the same thing. It doesn't matter what letter we choose, okay? It's still representing the same set of ordered pairs, assuming, of course, that the domains are the same for all of these. Okay? So the first three are the same thing. Now the last one, remember when I say f of x, that's just a more complicated way of writing f or y. So there it's the same as well. So all four of these things are saying exactly the same thing. They're relating the same, they are determining the same set of ordered pairs. They are the same function. Now, function notation, actually, we've seen part of it with the f of x part, but actually in function notation we have this notation here, and we would read this, the function f, you read the colon as maps, the function f maps the set D into the set C by the rule f of x equals some given rule. Now this arrow here ought to look kind of familiar. We got a set D and an arrow and a set C. Well, the set that we start with, D was chosen on purpose there, for domain. So this D is the domain. The C is the codomain. Think of that as the target set. And you would think probably that C ought to be the range, but not necessarily. The range has to be a subset of C. So C might be the range, but it might be some bigger set that contains the range. Now, and then the rule is given by some formula. The thing that's really nice about this notation is, especially that first line, is right off the bat it tells you what the domain is. It tells you at least what kinds of first coordinates we have and what kinds of second coordinates we have. And in the case of first coordinates, it actually tells you explicitly all of the first coordinates that are used. It doesn't actually tell you all the second coordinates that are used, but it tells you what kind of things they can be. They have to be in this set C, the codomain. Let's look at an example. We read this, the function f maps the set of real numbers into the set of real numbers by the rule f of x equals x squared. Okay, so when I see that first R, that tells me that my first coordinates have to be real numbers. So, for example, non-real complex numbers are not allowed. People are not allowed. Desks are not allowed. It's got to be a real number. And then the output has to be a real number as well because of the second R up there. Now, the second R tells us that the output's a real number, but it doesn't tell us if every real number is going to show up or only some of the real numbers. Maybe half of them, maybe all of them, maybe just one of them. But it's going to be a real number. It's not going to be something besides a real number, like an imaginary number or something like that. The first coordinate, first part there, the first R, is the domain. So it tells us that not only are the first coordinates real numbers, all real numbers actually are used. When that first number the domain is the real numbers, we say it's a function of a real variable. In other words, that the values that the variable x can take on are real numbers. The second R says that it's a real valued function. So the values, that is the y values, f values, outputs, are real numbers as well. So this is a real valued function of a real variable. Now, notice that the domain is all real numbers, so all real numbers get used. The codomain is a set of real numbers, but that does not imply that every real number is actually used. In this case, when you square a real number, you always get 0 or a positive, but never a negative. So in this case, the outputs are all the non-negative real numbers, so the range is actually the interval, the closed interval from 0 to infinity, bracket 0, comma, infinity, open parentheses. So the rule tells us that the output then is the square of the input. Okay, so you know, as you get into more advanced math classes, the functions maybe not just are not necessarily mapping real numbers to real numbers or just numbers to numbers at all. They can be mapping all kinds of objects to all kinds of objects. And that first line up there really is helpful for keeping track of what's going on. Okay, let's do one more definition. We say that a function f, say f is a function mapping a set D into set C via the rule f of x equals some rule. It's onto its codomain C if and only if the codomain equals the range. In other words, if the codomain is actually all used up as second coordinates, every bit of it is used somewhere as a second coordinate, then we say that it's onto that codomain. And we might also use the word surjective for that. And here, we're not going to talk about this a lot, but when we do, it'll be we'll use the word onto in here. So let's look at some examples. So the function f mapping the set of real numbers into the set of real numbers via f of x equals x cubed is onto the set of real numbers. If you start with a real number and you cube it, you not only do you get a real number, that eventually you will use up all the real numbers. But as we've seen, the function g mapping the set of real numbers into the set of real numbers by the rule g of x equals x squared is not onto the real numbers because, as we have seen, its range is just from 0 up to infinity, and so there are some real numbers that are not used, specifically the negatives, and so then it's not onto the real numbers. Now, really, onto is more of a description of the codomain than it is the actual ordered pairs, or rather how they compare to each other, because you can make any function onto. All you got to do is take this codomain and just whittle it down to the actual range, throw out the extra stuff. For example, we can make g onto by changing the codomain to the interval 0 to infinity. Okay? If that doesn't change a single ordered pair, it just changes the codomain, and if we do that, then it is now surjective or onto that interval. So we generally talk about functions, when you see the arrow up there, we say into, and then if it's actually is an onto function, then we'll then we'll say that. So, again, let's look at another example, actually one we've just looked at. So the function f mapping the set of real numbers into the set of real numbers by the rule f of x equals x cubed. Now, on the one hand, the first line of the function is maybe the most basic and in some ways one of the most important, but because it tells us the nature of the input and output values. Okay? Sort of tells us where our x's live and where our y's live, if you want to think of it that way, or at least what kind of x's we have and what kind of y, what kind of first coordinates, what kind of second coordinates. And it's very explicit about the first coordinates that all of the real numbers are used in this case. But we oftentimes will leave out that line. So we might write f of x equals x cubed and just leave it at that. Now, if that's all we had for a formula, there could be many choices for the domain. For example, we could let the domain be all complex numbers. We can cube all complex numbers, and that would be okay. So then it would be mapping complex to complex. Or the domain could be all the real numbers, which is what it originally was. Or we could say, okay, I just want the non-negative real numbers. Or maybe I just want the integers or the natural numbers. Or I could just have a set with a couple of 2 or 3 points in it, like the set 1, 2, 3. Or anything else. There's lots of choices I could pick. As long as it makes sense to cube them, the formula would make sense. So if you don't see this first line, and typically we won't see this first line written in most of the books, problems, okay, or most of the problems that we encounter, we're going to make some assumptions. And our standard assumption for this class and any other math class you're likely to have is when this first line of the function notation is not present, we will assume that the codomain is a set of real numbers, first of all. So we'll automatically assume this last part. And we'll also assume that the domain is the largest possible subset of the real numbers, so that the given formula will send them to real numbers. Okay? So you basically want to think of the domain being all real numbers and the codomain being real numbers, unless there's something inherent in the formula that says that it will not take those real numbers to a real number, then we throw those out. And let's look at a couple of examples of where this might happen. So if I see the function f of x equals 1 over x, what's the domain? Well, I mean, again, it could be anything. It could be just the numbers 1, 2, and 15 if we wanted, or say just the natural numbers. But with the assumptions that we've made, there is a natural domain to this. So in other words, with our standard assumption, what is the natural domain of this function? See if you can figure that out, and then come back when you think you have an answer. Press pause now. Well, recall that our standard assumption is that the codomain is a set of real numbers. So we want to be able to, we've got to end up with a real number output. And we'll also assume that the domain is the largest possible set of real numbers that makes sense here. In other words, that the formula will send them to a real number. So what you really want to think of is start with the domain being all real numbers and throw out the bad stuff. Well, what's bad stuff? Well, bad stuff is any real number that the formula will not send to a real number. So what are we doing? We're just taking 1 and dividing by x. Can we always divide? Well, almost. There's only one number we can't divide by. What is it? Yeah, it's 0. So we can't divide by 0. So the domain is all the other real numbers, because every other real number will work. 1 divided by any number gives you a real number unless that number you're dividing by is 0. So the natural domain of this function is all real numbers except for 0. Notice I've used some set notation there, where I've used the standard symbol for the real numbers, and I took away the one number, 0. If you did this in interval notation, you'd have to write it this way, open parentheses, negative infinity, comma, 0, close parentheses, union, open parentheses, 0, comma, infinity, close parentheses. So notice that the left interval contains all the negatives, the right interval contains all the positives, but neither interval contains 0, and we want to union those two sets together to get the entire set, which is the same as all reals except 0. And in this particular case, it turns out that the range is the same. Okay? So this function maps the set of real numbers except for 0 actually onto the set of real numbers except for 0. And of course, this would also be true to not have the set of real numbers take away 0 on into just the real numbers here without the minus 0. But if I want it to be onto, then I need to have this target set on the right that I have. Okay, how about this one? What's the natural domain of f of x equals 1 over 2x minus 6? See if you can figure that one out. Press pause now, come back later. Okay, well, let's think about this a second. If we take the input, can we always multiply by 2? Yeah, that's not going to give us any problem. Can we always take something and subtract 6? Well, again, that's no problem. Can we always take 1 and divide it by something? Almost always, but we can't divide by 0. So, the thing that we're dividing by, 2x minus 6, cannot be 0. So, adding 6 to both sides of the equation, or not equation there, says that 2x cannot be 6, and dividing both sides by 2, we see that x cannot be 3. So 3 is the only number that makes the denominator 0, and that's the only number that's not allowed. That's the bad stuff. So the natural domain is all real numbers except for 3. You can write that interval notation as negative infinity up to 3, union 3 to infinity, and it's all open intervals there, so that we skip over 3. It turns out that the range is actually the real numbers except for 0. So this function maps the real numbers except for 3 onto the real numbers except for 0. Alright, let's look at another thing that might generate some bad stuff here, some things we have to throw out. What's the domain of the square root of x? Press pause now. Come back when you have an answer. Okay, you got your answer? Did you say that the bad stuff here is going to be the negatives? Because a negative number, when we take a square root, we can do it, but we don't end up with a real number in the output. Okay? And remember, our standard assumption is we must have a real number for the output. Okay, so if nothing is said otherwise, the real numbers have to be the codomain. And if you put in a negative, you don't end up in the codomain, and that's not allowed. So negative numbers are bad stuff. We have to throw them out. So we end up keeping the positives in 0. So the natural domain of this function is the closed interval from 0 to infinity. That's bracket 0 comma infinity parentheses. Turns out in this case that the range is also the same thing. It's 0 to infinity. Alright, now this next one combines the ideas of the last couple of examples. See if you can put this together yourself. A little more complicated because it puts together a couple of things that we've done here. See if you can figure this out. Press pause now. Okay, now you're back. If you look at this here, there's a couple things that could give us problems. First of all, we can take any number, subtract 3, no problems there. We can take any number and square it, and we can take subtracting 16. That's no problems. There's only two places where we could have a problem. One is we take the square root. We can't take the square root of a negative. So the x minus 3 cannot be a negative, means it has to be greater than or equal to 0. And the x squared minus 16 cannot be 0 because then we would be dividing by 0. So we have x minus 3 has to be greater than or equal to 0, and x squared minus 16 is not 0. So on the left one, if we add 3 to both sides, we get x is greater than or equal to 3. And at the same time, x squared is not 16, which means x cannot be negative 4 and x cannot be positive 4. So we have to start with all reals. We throw out x equals negative 4. We throw out x equals positive 4. And we throw out any x's that are less than 3. Well, if we start by throwing out the x's that are less than 3, we've already thrown out x's negative 4, so that one really didn't matter. But we do have to throw out x equals positive 4 as well. And so we get x's are an element of the set, close bracket, 3, comma, 4, open parentheses, union, open parentheses, 4, comma, infinity, and then your parentheses as well. So do not include, notice that does not include the 4, and of course not infinity, but it does include the 3. And so that's the domain. And this is not easy to see right off the bat here, but it turns out that the range turns out to be all real numbers except for 0. Not quite obvious, but it is true. So when we're trying to determine the domain or natural domain of a function, what do we need to remember? We need to remember that dividing by 0 is never defined. 0 to the 0 power and 0 to a negative power is undefined. And taking an even root of a negative number does not produce a real number. And so those things are problems. Taking an odd root of a negative, however, is okay. So, for example, a cube root in a function is not going to restrict the domain any. But a square root in there could have some restrictions, or a fourth root would be like a square root as well. Now let's go back to this a minute. Suppose we have this function f, which maps the interval 0 to infinity into the real numbers by the rule f of x equals square root of x. That's the principal square root of x. And we have a function g, which maps the real numbers into the complex numbers by the rule g of x equals the square root of x. So are these the same functions? Remember, functions are a set of ordered pairs. Are these the same It's because it's a relation, right? So are these the same set of ordered pairs or not? Let's see if we can do this. Can you find a point in G that's not in F? If so, write it down. If it's not possible, say so. Okay? If you write a point, can you find a point in F that's not in G? Again, if you can find one, write it down. If it's not possible, say so. And then finally, let h of x be the square root of x, and nothing else was given above. Does h assume to be the same as f or g, or maybe neither one? Press pause and work this one out now. Well, no, these are not the same functions because they're not exactly the same set of ordered pairs. So how about a function in G that's not in F, a point that's in G that's not in the function F, and that would be -1 comma I, our imaginary unit I. So remember that the square root of -1, we call that I, which is not a real number, but it is a complex number. -1's a real number, I is a complex number, and the square root of -1 is I, so that is an ordered pair in G. That's not an ordered pair in F. It satisfies the rule, the square root of -1 is I, but -1 is not in our domain, 0 to infinity, and I is not in the codomain, the real numbers. So that's not one of our points that's in F. Give a point in F that's not G, well, that's not possible because every point in F is also in G. Notice that the domain of F is a subset of the domain of G, and of course the codomain likewise in F is a subset of the codomain in G. So remember that functions ultimately are sets of points, so the function f is actually a proper subset of the function g. Now when I just see h of x equals square root of x, the formula alone could indicate f or g or any number of possibilities depending on what we want to pick for our domain, but our standard assumption is that h is the same as f, that the codomain is the set of reals, and the domain is the largest possible set of reals that makes sense, which is exactly what f is. So, same two functions here. We say that if a relation f is a subset of a relation g, we say that g is an extension of f, and f is a restriction of g. So if we think of starting with the function f, which is the square root of function in the real numbers, basically, we can extend it so that the domain is not just the positives and 0, but actually all real numbers, as long as we extend the codomain to include all the complex numbers. Then we have extended our definition of what we mean by the square root, and we have extended to a bigger number system. And so this allows us to increase the set of ordered pairs, so that we kept all the ordered pairs we started with, but now we've added in some new ordered pairs, like for example -1 comma I. Okay, and so we have extended this by increasing the number of ordered pairs that we have. Now, on the other hand, if we think of starting with G and starting with all real numbers for the input and allowing complex numbers for outputs, and we want to cut it back to a smaller domain, that's called a restriction. So we start with G and we restrict the domain to be not all real numbers, but only the non-negative real numbers, the interval from 0 to infinity. We have restricted the domain, and of course we're probably going to restrict the range when we do that as well, but at least we've restricted the domain or the range 1, so that now we have a smaller set, a subset of points. Okay. Notice that the function notation f of x, f parentheses, x parentheses, f of x does not mean f multiplied by x. It looks a little bit like it, but it does not mean that in this context. F of x does not mean f multiplied by x. F of x does not mean f multiplied by x. Should have a video on me where me jumping up and down and saying that. This is very important. So instead, what it means is it takes your x value as your input, whatever's in the parentheses, and then the output is f of x, or f, or y. Because of this, f of x is one single thing. It's not an f and an x. It's really just an f. The whole thing together, f of x, is just f. Okay? It's just y. It's just the output. They are not separate, and we cannot separate them. So when we're doing this, for example, solve an equation, you can't divide by the x or divide by the f. The f of x is f. It's one thing. So f of x is just another way of writing f or y or whatever we want to call the output or second coordinate. So f of x is the general output for an arbitrary input x. F of 5 is a specific output coming from the input of 5. So f of 5 is not 5 normally. Okay? It's not an input. F of 5 is f. It is the output. Which output? The one that has an input of 5. So the ordered pair is 5, comma, f of 5. Alright, now the next thing we're going to do is we're going to look at some examples of working with some function notation in some of the different contexts that we've looked at for functions and relations. And there are two things that we're going to be doing with this that are fundamentally opposite processes. So if I say f of a number equals blank, for example, f of 0, this is asking us to find f of 0, that is to find the specific f, the specific y, the specific output, the specific second coordinate, when we have that specific input of x equals 0. Or we could put a different number in there. F of 3 would say find the specific f, y, output, whatever, when the input is 3. Now, since the relation is a function, there will only be one value for that output. That f depends completely on the choice of the x. That's why this notation is used. So when you say f of a, we're saying the f depends on a. Okay, so once the a is chosen, the f that goes with a is automatically fixed by the formula or table or however the function's given. Assuming, of course, a is actually in the domain. So there's going to only be one answer to this. Okay? If the input is actually 0, like it is here, then what are we talking about? We're talking about finding a second coordinate where the first coordinate is 0. Well, if you think of this in terms of a graph, a Cartesian graph, the first coordinate is 0, that means your x is 0, that means you're on the vertical axis, the y-axis. Okay? And what it's asking you to find is the y-coordinate that goes with that point. So in other words, what we're doing is we're finding where the graph crosses the y-axis. That's called the Y-intercept, which is actually an ordered pair. And what we want to pull off of that is the second coordinate. So it's the y-coordinate of the Y-intercept. Contrast this with the next one. When we say f of x equals 0, that's saying f equals 0, or y equals 0, or output is 0. Notice in the first one, when I said f of x equals 0, I'm going to say f of 0 equals blank, then I'm saying x is 0. X is the input. The input is 0. What is the output? Okay, that's what we're trying to do. This is backwards. Down here, when I say f of x equals 0, I say f is 0, output is 0, y is 0. I know the second coordinate is 0. I want to find out what the first coordinate is. And of course, we could put any number we want in there besides 0. This may have more than one solution, because there could be in a function where we have a second coordinate that comes from two different first coordinates. That could be possible. If the output specifically is 0, what we're talking about? We're talking about finding a place, graphically, where we know the second coordinate is 0. Well, think about it. Where are the second coordinates 0? Okay, when y is 0, we're on the x-axis, the horizontal axis. Okay, so what we're trying to do is we're trying to find when the graph crosses the horizontal axis, the x-axis, we would call that a x-intercept, perhaps. And what we want from that is to find out, of course, what the first coordinates are. So what we're trying to do is we're looking for the x-coordinates of the x-intercepts. in a way just backwards to the previous type of problem. Now, here are a number of different exercises for you, several of them. We actually have 4 different functions. We have f of x is 3x plus 4, g of x is x squared plus x plus 5. So f and g are both given by formulas, different formulas. H of x is given by a table, and k of x is given by a graph. These are not the same function. We obviously have different formulas for f and g. Any formula that we would have for h would not necessarily be the same as f or g, or when you graph h, it's not going to necessarily look the same as k, and the table for k is not necessarily the same as h or g or f. So this is a 4 different functions, and we can tell them apart by the letter. This is why it's very, very useful. Another useful thing about this function notation is we can look at this and we can talk about the function f, g, h, or k, and we know which one we're talking about by which letter we use. So I want you to figure out and evaluate these things here. Find the indicated values. F of 2, f of 3, g of 3, g of 0, h of 1, and so forth. And work out all these problems. It's going to take a few minutes. Go ahead and get your stuff ready. We're going to press pause, work through these, get an answer, then come back and check your work. Press pause now. So let's go through here and look at these. So for f and g, these are the same problems we did. We've just got the solutions here. F of x is 3x plus 4. G of x is x squared plus x plus 5. The first 4 problems, I'm giving you an input, and the formula is given for defines the function, and you're supposed to find an output. So the way you do that is, everywhere there's an x, or whatever letter is the input letter, in this case x, put a set of parentheses, and in the parentheses put what's in the parentheses to begin with in the problem. So for example, f of x equals 3x plus 4. What is f of 2? Well, you take 3x plus 4, put a parentheses where the x is, and put 2 in that parentheses. So it's 3 times 2 plus 4. Now just use order of operations and so forth to figure it out. 3 times 2 is 6, plus 4 is 10. So f of 2 equals 10. In other words, 2 comma, I should say 10. 2 comma 10 is part of the function. Typo, we'll have to fix that. F of 3, well, this time, same thing, but we put a 3 in the parentheses. 3 times 3 is 9, plus 4 is 11, so f of 3 equals 11. In other words, 3, 11 is part of the function, but it's not. But the order pair 3 and 11 is not the answer. The answer is just 11. It's just the second coordinate. It is just the f. It is the f when x is 3. Now, the next one I need to find the g. That's also the output, but it's of the function g. So again, you take the same idea, but it's a different formula this time. This time we have x squared plus x plus 5. And so we take the x and replace it by parentheses with a 3 in it. So g of 3 is 3 squared plus 3 plus 5. Square first, so it's 9 plus 3 plus 5. That turns out to be 17, so g of 3 equals 17. G of 0 then, as you can see there, works out to be 5. So when you have a formula and you want to evaluate, simply just replace the x by whatever is in the parentheses, and you're good to go. And then just simplify it. Okay, so here we go. Hopefully you worked this one out already. So for the table, this is actually the easiest one of all. But it's also the easiest one to get backwards. And my experience is that a lot of students, the first time I do this, will get it backwards for some reason. I don't quite know why, but they do. When I say h of 1, I'm looking for the answer to this is an h value. It's an output value. Where the h's are outputs. They're in the second line. So the answer is going to be down here in the second line. Well, which one do I pick? I pick the one that goes with the input of 1. So I start by looking at the x is 1. I find it. Whoop, here it is. X is 1. I've got it in red here. And the output then that goes with that is negative 2. So h of 1 is negative 2. I suspect some of you went backwards and said 0. No, that's looking it up backwards. The x is 1. what the answer is, the h that goes with that, the output, which is -2. Similarly, h of 2, I scan across here and find 2 in the first coordinate, find out what its second coordinate is, and it's 0. So be careful you don't get that one backwards. Be careful any of them you don't get backwards. Next, I have some following problems. Now, so far, all the problems are basically the same. So basically, the same in the sense that I'm giving you the x coordinate, or the first coordinate, the input, by putting it in the parentheses in the original problem, and you're supposed to tell me what the second coordinate is, the y value, or whatever letter it might be called, like in this case, k. Now, the way you do that from a formula, table, or graph is slightly different, but it's still basically the same idea. So when I'm looking at k of 6, I'm looking at the graph here, and I'm finding when x is 6. So I'm looking at a vertical line here at x equals 6, right here, seeing where that crosses the graph, which is right here at this green point here, and I see that that has a coordinate of 6, 1. I find out, take that point, go over and see what it lines up with on the y-axis, which is positive 1, and so the output is 1. So k of 6 is 1. That means the ordered pair 6, 1 is on the graph. K of 0 is -8. So I take all the points where x is 0, that's the y-axis here, and look and see where that crosses the graph, which is just once, because remember, this is going to pass the vertical line test if it's a function. If it's not a function, I wouldn't be using this notation. And it crosses at 0, -8, so the answer, k of 0, is -8. Now we're going to switch to a fundamentally different problem. It's a sort of the inverse operation, or opposite to the previous problems. All the previous problems I basically told you the input and asked you to find the output. Now I'm going exactly backwards. I'm telling you the output and asking you to find the input. So here I'm saying f of x equals 4. I'm not defining a new function f of x equals 4. I'm still saying f of x equals 3x plus 4, but I know that the f equals 4, the y equals 4, the f of x equals 4. So in place of the f of x, the f, the y, I'm putting the 4. So the 4 replaces the left-hand side of that equation. So I go to 4 equals 3x plus 4, and of course then the natural thing to ask is, well, what are the x's? So I just need to solve this equation for x. And what I can do is, hopefully you've seen this before, you can subtract 4 from both sides of the equation. If two things are equal, if you subtract 4 from them, they'll still be equal. And so that gives you 0 equals 3x. And then I divide both sides by 3, and we get 0 equals x, or x equals 0. So f of x equals 4 is going to happen exactly when x equals 0 for that particular f. So again, for that particular formula for f, if I let f of x equals 0, I'm putting 0 in place of f of x this time instead of 4. Again, I subtract 4, gives you -4 equals 3x, and again I divide both sides by 3 to get the x by itself on the right and get x as -4/3. So x equals -4/3, one answer. Now the next one actually has two answers. It's a little bit more complicated. Let g of x equal 5. So I've got 5 equals x squared plus x plus 5. I subtract 5 from both sides and I get 0 equals x squared plus x. Now I'm going to use a property of numbers that we looked, a property of 0 that we looked at earlier. If I take the right side and I factor it using the distributive property, which we have talked about, then I factor out the x, I get x times x plus 1. Now I have something in the form 0 equals a times b. Well, we know one of the nice properties from arithmetic that 0 has is a times b equals 0 means either a equals 0 or b equals 0. Or it could be both, which is included in the or. Okay? But at least one of them has to be 0. So in this case, that says x equals 0 or x plus 1 equals 0. And of course that means on the right hand that x equals 1. So if x equals 0 or x equals 1, negative 1, excuse me, then that would make g of x be equal to 5. And so we get two solutions. So we said g of x equals 5 implies either x equals 0 or x equals -1. Notice you do need to say something about x equals 0 or x equals -1, or perhaps you could say it is x is an element of the set containing 0 and -1. But it needs to have a verb. It needs to have that equals or is an element of. You can't just write 0, -1 because that's not a statement. You need to have a statement which needs our subject and verb there. Okay, similarly going on, again, h of x is going by the table. By the way, notice again that the letter tells us whether we're looking at the table, a particular formula, the other formula, or the graph, right? So h was the one that was given by the table, and we said h of x equals 1. This time it says h of x is 1, or h is 1, the y is 1. And so we find the 1 in the output row, and there it is in purple, and you see that its corresponding input is 0. So we can't just say 0, we have to say x equals 0. So this says h of x equals 1 implies x has to be equal to 0. On the other hand, if h of x equals -1, there are two choices. You can see them in red as we look through the second row to find -1. There are two of them and two possibilities for x, either x equals -2 or x equals 3. How about from a graph? K of x equals 8. So that says k is 8, y is 8. The output is 8. Well, if the output is 8, that means it lines up with 8 on the vertical axis. So all the points that do that are actually on this horizontal line. I think you can maybe see it here in the graph where this is a darker blue line here, a little bit thicker. That's the line y equals 8. And where does it cross the graph? Well, it crosses the graph two places. This little green dot right here is at -8, 8. And this one over here is at 8, 8. So what are the x values? Well, bring down and see. We should bring this down here, that's -8, and we bring this one down here, that's +8. So x equals -8 or x equals +8. What about k of x equals -7? Draw a horizontal line at -7, so y equals -7 is this purple line down here, it's horizontal. Crosses the graph in these two green places, and they are, what are their x's that go with it? Well, -2 and +2. So -2, 7, -7, and -2, -2, comma -7, and -2, comma +7 are 2 points on the graph. That's the ones we're looking for, but the answer, what we want to say is, what are the x values? So x equals -2 or x equals +2. So here we are back to the same slide we had before, with all the answers recorded together. So, after looking through this lecture, both parts 1 and 2, and studying this a bit, what should you be able to do by now? Well, you should be able to define a function. You should be able to look at a relation and tell if it's a function in any relationship that we've looked at, whether that's set notation, tables, arrow diagrams, verbal descriptions, rules, dynagraphs, Cartesian graphs, formulas and equations, and by just looking at it in that form you should be able to tell if it is a function or not. So you should have a good understanding of that. You should understand function notation, what it means, what you can do with it, what you can't do with it. You should be able to determine if a function is onto a stated codomain. You should be able to find the natural domain and range of a given function if it's not given to you in the statement of the function name. If they leave off that first line, you should be able to tell what it is anyway, because we have some standard assumptions that we apply. We need to be able to identify what we mean by independent and dependent variables and independent and dependent coordinates. And we should be able to evaluate a function at a particular input value. So in other words, be able to tell what f of a is. So it's basically finding outputs for given inputs. And we should be able to go the other way. So if we have f of x equals a, equals a constant a, and then we should be able to find the inputs for x that make that true, that make that work. And f could be given by any of the ways that we've seen earlier. You should still be able to do this in terms of evaluating it. Okay, so that gives us a pretty good overview of the basic parts of functions. We're going to be spending many days talking about functions. In fact, the whole rest of the course really is talking about relations and functions. and we'll be using these different notations and these different representations as we go forward through the class.